Bungee! Jumping!
What now?
How do we get down?
Blood is rushing to my head.
Next, we are going to talk about stacks. Because I am upside down, the stack must be as well. So the stack top will be at the bottom, and the bottom will be at the top.
Push Q %RDX will add 8 bytes of %RDX to the top of the stack. If we pop Q %RDX, this will move the stack top pointer back up to a higher address. The bits will stay, but be declared empty, leaving a ghostly value. %RSP always contains the address of the top of the stack. When we push a register onto the stack, it's the register's value that is on the stack, not the register itself. So if the value in that register changes, the value on the stack does not.
I need to always know the size of a variable that I'm creating. However, if you don't know the size, you can malloc space. Say I had a struct called person. I could then say person Katie equals malloc size of person. This would give me the amount of space necessary. These structs occupy a contiguous part of memory large enough for all its parts. The space it takes is always a multiple of the size of the largest field type. If you want to refer to a specific part of a specific struct, you could say Katie arrow gender equals F. Calloc is similar, but takes in 2 parameters, and void *calloc person size of jar. Malloc and calloc go in the heap. Realloc can resize other allocs.
As you work, the stack and the heap will grow towards each other. If they run into each other, you get an overflow and your program will crash. Because of the size of things today, this will probably never happen unless you have it running long enough without ever freeing it with free person.
Call calls another function. This pushes the address of the instruction after the call. For example, call my function. This is very useful since without the ability to call functions, everything would have to be in one long strand, and not even I am that much of a masochist. Ret is the return you would see at the end of non-void functions in C files. The return value is always %RAX if the value is small enough. This pops into the %RIP or program counter. Ret also pops the address of the next instruction. NOP does essentially nothing. It just adds space at the end of code to make it come out to a nice amount of space. It's like padding, except it's in the code instead of in the memory. LEAQ takes the address of the first operand and puts it in the value of the second. For example, LEAQ for %RAX, %RDX would take %RAX's value of 13, add 4, and put it into %RDX. This is different than move. Move Q for %RAX, %RDX would add 4 to what's in %RAX and then go to that memory address. Take what's there and then put that in %RDX. So in this example, %RDX would end up holding whatever is in address 17. LEAQ is often used for doing basic multiplication and addition on operands. IMULQ and MLUQ multiply A and B for signed and unsigned integers respectively. These can also just have one operand. In this case, I will multiply by %RAX and put back in the operands stated. For example, IMULQ %RDI will give you the signed multiplication of %RAX and %RDI and put it in %RDI. These are fairly straightforward. You can do the same things with parentheses and ampersand and $sign to work with addresses or direct numbers. Most work with the numbers as a whole, and 3 are operations on bit vectors.